We address and clarify in this work fundamental methodological aspects of end-user elicitation, enabling such studies to be run with confidence, correctness, and scientific rigor. End-user elicitation has become exceptionally popular since the advent of the method in 2005 with the initial phrasing of guessability studies, where guessability specifies the situation where the user of an interactive system, despite a lack of knowledge of the symbols employed by that system, can still access and use it. The most common application of end-user elicitation has been uncovering users' preferences and mental models for gesture input, such as user-defined gestures for surface computing, an iconic study from 2009 that consolidated the method. During end-user elicitation, participants are presented with the results of a system function, called the referent, and are asked for the action or symbol, called the sign, that would bring about that result. Since the introduction of the method, several enhancements have been proposed, such as new measures of agreement and co-agreement, techniques to reduce legacy bias, distributed end-user elicitation with crowdsourcing, examination of chance agreement, and development of automatic procedures based on dissimilarity functions. A systematic literature review from 2020 revealed more than 200 academic papers having employed the end-user elicitation method to that date. However, specific concerns have been raised in the scientific literature regarding specific aspects of the end-user elicitation method. For instance, Theophanis Tsandilos claimed that the established measures of agreement calculation, such as the agreement rate, do not take into account chance agreement. In our paper, we address such concerns by making several fundamental contributions to the end-user elicitation method. Our first contribution is a formal operational model for end-user elicitation studies in HCI with 6 steps. In step 1, upon the presentation of a referent, the participant forms a mental model of the system effect corresponding to that referent. In step 2, the mental model of the system effect is instantiated into a mental model of the command that the participant is asked to propose to effect the referent just demonstrated. During steps 3 and 4, the command is articulated into an actual proposal that is captured by some acquisition device or logged by the experimenter. In step 5, a classifier distills a set of signs based on the similarity among the descriptions of all elicited proposals. In step 6, which is independent of step 5, a characterization procedure is used to compare descriptions of the elicited proposals. A core component of end-user elicitation is the notion of agreement, for which several measures have been employed. For example, in a study of 20 participants, if 15 participants propose the same action or symbol while the remaining 5 propose a different one, then the agreement rate measure computes to 0.605. Our second contribution is showing that the notion of agreement employed in end-user elicitation studies can be formalized mathematically as a tolerance relation that respects reflexivity and symmetry. Reflexivity means that any proposal A is in agreement with itself. Symmetry means that two proposals A and B are in agreement if and only if B and A are also in agreement. Prior work assumed agreement to be transitive also, which means that if proposals A and B are in agreement and B and C are in agreement, then it must follow that proposals A and C are also in agreement. Although convenient, the transitivity of agreement is not a valid assumption for end-user elicitation studies. Consider, for example, 3 hand gestures A, B, and C performed on a touchscreen to select options using the finger count technique. A simple dissimilarity function could compare these hand gestures with the difference in the number of finger touches detected on the screen. This means that A and B are at a distance of 2 finger touches, B and C at a distance of 1, and A and C differ by 3 touches. If we choose a tolerance of 2 fingers touching the screen, then A and B are in agreement, B and C are in agreement, but A and C are not. In our paper, we provide empirical evidence from approximately 90,000 gestures collected from nearly 500 participants, showing that agreement is not transitive under commonly employed dissimilarity functions such as the Euclidean distance, dynamic time warping, or the point cloud dissimilarity. Mathematical relations that respect all the 3 properties are called equivalence relations. Mathematical relations that respect reflexivity and symmetry are called tolerance relations. Agreement in end-user elicitation studies is a tolerance relation, which is a fundamental theoretical discovery with many implications. Our third contribution regards chance agreement. In a 2018 paper, Theophanis and Dilas argued that agreement measures commonly used in elicitation studies, such as the agreement rate, do not consider agreement occurring by chance and, therefore, their values may be artificially large. The concept of chance agreement comes from inter-rater reliability studies, which have been traditionally implemented using nominal data and raters assigning subjects to predefined categories. For such tasks, and especially when the number of categories is small, Jacob Cohen argued that a certain amount of agreement is to be expected by chance. If two raters are unclear about the category to choose, but they still need to make a choice, chance agreement can occur because of their limited options and potential bias for or against specific categories. In our paper, we provide arguments that chance agreement is an issue for equivalence relations only, which the agreement relation is not. This aspect becomes clear once we examine the differences between end-user elicitation and inter-rater reliability studies. One important difference is that inter-rater reliability studies operate with a fixed list of categories defined before the study. However, the list of categories or signs is one outcome of end-user elicitation known only after the study has completed. Also, Cohen's quantification of the probability of chance agreement is based on the assumption that the categories of the nominal scale are independent, mutually exclusive, and exhaustive. These assumptions can be verified only when the categories are known, which is only after an elicitation study. Another important difference is how agreement is defined. Having a fixed set of predefined categories on a nominal scale makes the transitivity of agreement a consequence of agreement formation in inter-rater reliability studies, whereas we showed that transitivity should not be assumed for end-user elicitation. Furthermore, data and end-user elicitation studies are not nominal but ordinal interval and ratio too, which changes the game completely. In their Handbook of Inter-Rater Reliability Studies, Guillaume-Gouet notes that for interval or ratio data, the very notion of agreement must be revised. Given the large number of different values a score may take, the likelihood of two raters assigning the exact same score to a subject is slim, and, with agreement no longer referring to an exact match, the notions of chance agreement and percent agreement evaporate. Our fourth contribution regards statistical tests for end-user elicitation. We identify three distinct models of agreement analysis: expert, codebook, and computer. In the expert model, the knowledge about which proposals are similar is defined by an expert. In the codebook model, experts are not available, and the task is left to the members of the research or design team. This model is by far the most ubiquitous in published elicitation studies. In the computer model, a computer program is employed to automatically compute the dissimilarity between any two elicited proposals. We also run extensive simulations of 16 statistical tests for within and between subject designs of end-user elicitation studies and report estimations of type 1 error rates and statistical power. For more details and other clarifications regarding end-user elicitation studies, please see our ACM Tokai paper. Thank you for watching.